Hi and welcome to this special lesson. We're dealing today with shapes of molecules and ions. Your lesson objectives for today are: understand how the shape of a simple molecule is determined, understand that lone pair repulsion has influence on the bond angle. At the end of the lesson, you should be able to explain how the shape of a simple molecule is determined. Also, you should be able to explain that lone pairs of electrons repel more strongly than bonded pairs. For the exam, you need to explain and predict the shapes of and bond angles in molecules and ions. Your keywords for today are trigonal planar, tetrahedral, octahedral, and linear. Valence shell electron pair repulsion theory, better known as VESPA. And this is the post definition. Electron pairs in the valence shell of the central atom of a molecule will stay as far apart as possible to minimize the electrostatic repulsion between electron pairs in the valence shell. The electron pairs are oriented with the maximum separation in space so as to minimize the Coulombic repulsion of electron clouds. Wow. So what can we do with the electron pair repulsion theory? Well, we need to divide the problem into two parts. In the first part, we're going to look at structures that don't contain lone pairs, while in the second part, we're going to look at structures that contain lone pairs. So, if I start with structures that don't contain lone pairs, I like to talk about regular shapes. We're dealing here with molecules that only contain bond pairs. And the examples that we're going to look at are linear, trigonal planar, tetrahedral, Trigonal Bi Pyramidal, and octahedral. Bond angles and examples you can see on the screen. And we will start with the linear compound. Although you might think that beryllium chloride is an ionic compound, beryllium really forms mainly covalent bonds. And as you can see in this example, beryllium shares an electron with each of the chloride ions. The only way for beryllium chloride to get the non-bonding electrons, and these are the electrons that the chlorine doesn't use for bonding, as far away as possible, is by using a linear shape of 180 degrees. In this structure, there are no lone pairs, and there are only two bonded pairs. They are the green and the red dot on the left and right hand side of the beryllium. So it's a bit like you wanting to put your hands away as far away as possible. The only way you can do this is by having your hands forming a 180 degree angle with your body. Let's have a look what is happening when we add an additional atom . So we started with a 180 degree angle, and we're going to add an additional atom to the structure. As you can see in the animation, the preferred bond angle is going to be 120 degrees. An example is aluminium chloride. Again, this might seem that this is an ionic bond. Like beryllium, aluminium prefers to make covalent bonds. And in the case of aluminium chloride, aluminium will share 3 of its outer electrons with 3 chloride atoms. So in this case, you got 3 bonded pairs, no lone pairs. Therefore, for aluminium to keep the chlorine atoms as far away as possible is having them under a 120-degree angle. We call these structures trigonal planar. Going from aluminium chloride to a structure with 4 groups around it, you can see from the animation that we're going towards a tetrahedral structure. Well, if you go on to Moodle, you can find the mathematical explanation why the bond angles in a tetrahedral structure are 109.5 degrees. An example of a tetrahedral structure is methane. The carbon outer electrons, 4 of its outer electrons, are teaming up, sharing electrons with 4 hydrogen atoms. The only way to get the hydrogen atoms as far away as possible is by going for a tetrahedral structure. Keep in mind, if this was all as a 2-dimensional problem, the hydrogens would only be 90 degrees away from each other. So in a structure where you have 4 bond pairs, no lone pairs, the preferred bond angle would be 109.5 degrees and the structure is called tetrahedral. So what are we doing if we have 5 groups around it? Well, an example here is phosphorus Roman numeral 5 fluoride. The only way that the 5 fluoride groups can be as far away as possible is by having 2 of them in an axial position and the remaining 3 in an equatorial position. The structure that you get here is what we called Trigonal Bi Pyramidal, Trig BP. You can see from the drawing that the 3 fluoride atoms in the equatorial plane have a bond angle of 120 degrees. The bond angle between both axial fluorine atoms is 180, therefore the bond angle of the axial and the equatorial fluorides is 90 degrees. And we can expand this story by having 6 fluorides around it. So if we look at the example of sulfur fluoride, sulfur has the ability to extend its orbitals, therefore it can form bonds with 6 fluoride atoms. The only way to get the 6 fluoride atoms around the central sulfur is by going for an octahedral shape. We have 6 bond pairs, no lone pairs. All the fluoride atoms are under 90-degree angle. 4 of them are equatorial, 2 of them are axial, and we call this shape octahedral. A bit more tricky is when we're dealing with what we call irregular shapes. These are shapes where 1 or more lone pairs play an important role. Now if we look at the picture on the left on the screen, we see that we got 2 bond pairs. If we replace one of these bond pairs by a lone pair, the bond angle becomes larger. If we replace the final bond pair by a lone pair, so we are on the right hand side of the screen, we have 2 lone pairs and they repel even more. So going from left to right on the screen, the repulsion is increasing, therefore the bond angle is increasing. And this is quite an important concept that you need to know for the exam. An example of an irregular shape is ammonia. If we look at nitrogen, nitrogen has 5 electrons in its outer shell, but it cannot extend the octet rule, therefore it can only use 3 of its outer electrons to form bonds. The remainder of the electrons is what we call lone pairs. We need to look at ammonia like that there are 4 groups around it. One of the groups is the lone pair, the other 3 groups are the hydrogens. So the structure that we can expect will be tetrahedral, but a special case of tetrahedral. Because as we saw in the previous slide, the bond angle between the lone pair and a bonded pair is larger than between 2 bonded pairs. So the bond angle between a hydrogen, nitrogen, hydrogen will be 107 degrees, and we will call this structure pyramidal. Water is an example of a molecule where you have 2 lone pairs. Again, we got 4 groups around it, 2 hydrogen atoms and 2 lone pairs. So the shape that we get is based on a tetrahedron. Because we have 2 lone pairs in green repelling each other, the bond angle now will be 104.5 degrees, and we call this shape angular. Another name for this shape will be bent. A little bit more of an exotic case is, for instance, xenon tetrafluoride. We have 4 bonded pairs between the xenon and the fluoride, but we also have 2 lone pairs. Again, we got 6 electron pairs, so the shape will be based on an octahedral. And as you can see, the lone pairs are axial and the 4 fluoride atoms are equatorial. This is a very special case that you will not see in the AS textbook, but it's worthwhile just to use your thinking skills and see if you can explain what type of structure will be formed. It is of course quite important that you can predict and calculate the bond angle and the shape of molecules and ions. I like to look now what is happening with ions. And I'm going to start with my nitrogen atom. I've got 5 electrons around it, and I'm going to look at 2 specific cases of nitrogen ions. On the left hand side, I've got the ammonium ion. Nitrogen has gained a hydrogen. It's a bit of a mistake. Nitrogen has not gained 1 hydrogen. Nitrogen has gained 4 hydrogens and has the positive charge. Another example could be the amide ion. In this case, hydrogens have been added to the nitrogen, but only 2, and therefore the NH2 will be minus. So can we predict the structures? So drawing out the dot and cross diagram for the NH4+, you can see immediately that there are 4 groups around it, so the structure what you would predict is based on a tetrahedron. If you look very closely to the amide ion on the right, you will get a similar shape, because you've got 2 hydrogens around it, and you've got also 2 lone pairs around it. So in total you have 4 groups. So the structure that you would expect for ammonium ion is tetrahedral, 109.5 degrees, and the structure that you would expect for the amide ion is around 104.5. Compare the amide ion on the right hand side with a water molecule. The only difference is we got a nitrogen instead of an oxygen. So in overview, if I'm looking at 3 different structures containing nitrogen, in ammonia, NH3, we can see that the structure will be pyramidal. Based on 1 lone pair, the structure will be 107 degrees. In the case of ammonium, there are no lone pairs left. We got 4 bond pairs, so the structure will be 109.5 degrees. In the amide ion, NH2-, we got 2 bond pairs and 2 lone pairs. We can call this structure angular or bent, and the bond angle will be around 104.5 degrees. So what do we do with molecules with double bonds? Well, it's being done in the same way as other molecules and ions are sorted. Clearly in CO2 there are no lone pairs, therefore what you will see is that the bond angle will be 180 degrees. Yeah, the oxygens want to be as far away as possible, so the shape will be linear. And we can look at some more exotic examples on the next slide. SO4 2-. The structure that you would expect is tetrahedral, and the bond angles will be 109.5 degrees. Bromine tetrafluoride. 3 bond pairs, 2 lone pairs, it's T-shaped. Now this is a very special case that you will not see at A level. Bromine pentafluoride, another exotic one. It's another one you will not see in this course. The reason that I show you is, can you make predictions what the shape of these structures will be? And as you can see very clearly with bromine trifluoride and bromine pentafluoride, both structures are based on the Trigonal Planar structure and the Octahedral structure. So, test questions. Can you draw the structure of the following compounds? And the best way of doing this is state the number of bond pairs, state the number of lone pairs, state the bond angles, and then draw and name the shape. Answers for this exercise I like to have on Thursday when you come into my lesson, and then we will take it from there. Thank you for your attention, and I'll see you Thursday. Bye!